We're going to travel first to Asia Pacific, move on then later after lunch to Europe, and we will conclude in the Americas. And we're going to be asking where momentum is especially strong, what's driving promising applications in each region, and how different actors are working together. We heard some great discussion of that just now in the panel. We're going to take a deeper dive on that as well, with respect to the three regions, and also ask what we can learn from each other, because just now we heard, and I think this is a message that's been reiterated at AMTC often in the past as well, the lessons learned from one region are very important for other regions, and we want to be taking a closer look at that as well. And we're going to do all of that with reference to concrete, hands-on business cases presented by leaders in the AM field. And of course, we also look forward to hearing from you, dear ladies and gentlemen, in this session. We're going to be taking questions at the end of each of our regional discussions. So let us now begin, and it's my pleasure to introduce our panel. All three are with us virtually, and I begin with Dr. Hock, Assistant Vice President at the Singapore-based global marine and offshore engineering group Sembcorp Marine. Very glad to have him with us on board. Also with us are Dr. Cailan Tian, Project Manager and Head of AM at the Chinese rocket firm Deep Blue Aerospace. And we're going to hear from Dr. Guoying Zheng, Vice President and Head of AMDC at the Singapore-based aerospace company ST Engineering, which provides solutions across the aircraft life cycle. And I will now just say a very quick word about our format before I ask our first presenter to begin. I will ask all of you to please share not only what you're achieving with AM quite concretely, but also what challenges you're facing and how you have overcome them. And I'm also going to ask you to give us your perspective on key drivers that help you integrate and scale AM, and on collaboration. Who are your key partners and why? And now, and here comes the tough part, I'm going to ask everybody to do all of that in 12 minutes or less. So let us begin with Dr. Hock.
Thank you.
I'm sorry, I said you were virtual, and here you are live.
Oh, yeah.
Excuse me. Welcome. It's great that you're with us live, and forgive me for that
No worries.
Error.
Hello, hello. Test, test. Can everyone hear me? Hi, very good afternoon. Pleasure. First of all, I'd like to thank the organizer, So we have Tum and Ericon, as well as EDB for having me here today to share with you on the topic on the application and opportunities of additive manufacturing in maritime and offshore space. So the format of my presentation, mainly in the next 15 minutes, I'll cover on these 4 key areas. First, I'll introduce about Sembcorp Marine. Then I'll talk about the application of additive manufacturing in the marine and offshore industry in general. Then I will share Sembcorp Marine's experience in additive manufacturing. Lastly, I will also touch about the challenges and future opportunities of AM in this space. All right, just a quick introduction of Sembcorp Marine. So at Sembcorp Marine, we provide innovative engineering solutions, products, and services to the offshore marine and energy industry. So we have 4 key business units. One is the repairs and upgrades. We have also the rigs and floaters. So basically, we are the designer as well as the EPCC contractor, the manufacturer for, let's say, drill ships, FPSOs, for example. Then we have the offshore platform business unit that look at the production platforms, oil and gas production platforms, as well as more recently in a wind farm, the switchboards in wind farms. And then we have specialized shipbuilding that look at specialized shipbuilding, such as very specialized vessels, such as a full electric ferry, RoPax. And then we also more recently going into the area of transporting new fuels, such as ammonia, hydrogen, as well as CO2, liquid CO2. So we are based in Singapore, so we have a few yards in Singapore. So we also have shipyards in Indonesia, in the UK, as well as Brazil. We also have a number of technology companies. So these are the design companies that are based in Norway. So all in all, we have 11,000 employees. We have delivered more than 500 offshore engineering projects. Every year, we service close to 400 vessels. And then we have a suite of solutions. So we have more than 400 over design solutions. So for a start, I thought it's important to set the context as to what is the difference between the ships, offshore structures, as compared to traditional products. So as you can see on the screen, so on the left-hand side, so if we compare consumer product, so ships fall under the box of engineering structures, including, let's say, ships or planes. So in terms of the manufacturing characteristics, unlike consumer product, we are highly customized. Ships are highly customized, where we produce them in very high mix, low volume. So the cost per unit are also very high. And in terms of the lifespan of the product is much longer than the traditional consumer products. Next, I'll move on further to in terms of the complexity of ships or offshore products. On the left, on my left-hand side, you can see the comparison in terms of measuring the complexity as well as the construction time, comparing the three engineered products, automobile, the aircraft, as well as a typical offshore vessel. So from this diagram, you can see that in terms of the complexity, as well as the construction time, ships takes the longest time and is the most complex to build. So in Singapore, I think it was mentioned just now earlier by Leonard, we have a national initiative, a body that was set up called NAMIC, to accelerate the adoption of additive manufacturing, not just in maritime, but of course across the various sectors. Particularly in maritime, I will say that we started to look at 3D printing about 4 years ago. So you can see it started off with this on the left-hand side picture, where the MOU was signed between NAMIC as well as the Maritime Port Authority of Singapore, MPA, to start to look at 3D printing to be applied in the maritime sector. So moving on, the next 4 years, a lot of work has been done. So for that, I want to give the credit to NAMIC, who have, I would say, managed to pull in a very healthy ecosystem, build a very healthy ecosystem for AM ecosystem within Singapore. So you can see one of the examples of the GIP projects that they have done in the news release, what you can see. So they award funding to kickstart, the AM application in the maritime sector. So apologies for the very small boxes, but then what I'm trying to illustrate here is that you can see in terms of the whole ecosystem, maritime ecosystem comprising of ship owners and operator on the left-hand side, followed by the ship management, the supplier and the OEMs, and then we have the AM service bureaus. We have also the testing and certification bodies, followed by the IHLs, the Institute of Higher Learnings and the Research Institute. So you can see it's quite a healthy pool of ecosystem that's put in by NAMIC, and then to work on various applications. So in Sembcorp Marine, we are also involved. So you can see on the bottom left box, we are one of the consortium that got the grant. So what I want to mention in this consortium, what is interesting is that we managed to pull in not just the ship owners and the operators to try out additive manufacturing parts, to install additive manufacturing parts in their vessels, but we also managed to pull in members such as from the marine insurance as well as the OEMs. So everybody are, I would say, in general, very curious and interested in the technology. So I think that is the benefit of having a different stakeholders between the GIP projects to share experiences and then to understand what are the challenges as well as what does it take to scale, to implement or scale additive manufacturing in the maritime sector. So I've shared. So over here, what I've managed to pull in, consolidate some of through the various GIP projects. I think we are looking at quite a number of different parts on a vessel that is currently either they have already been 3D printed or the ongoing works are still ongoing. So, example, so it basically goes all around the entire vessel. On the left-hand side, on the right-hand side, we have the forecastle. On the main deck, we have some of the like Panama chokes, scrubber plugs, cam lock fittings, and then in the stern area, even propeller. People are already starting to look at printing propellers. And then in the machinery room or the engine room, we have many different types of use case application for these 3D printed parts. So I wanted to emphasize here, a lot of these parts that is being looked at now in maritime are mainly functional parts. Okay, so these are part of, it can be a partial of a whole system, just one single component of a whole system. So in Sembcorp Marine, basically 3D printing is one of the key components in the digital production process. So you can see in the middle, for example, under digital production. So we have, so basically we, in terms of, we are trying to make the manufacturing process smarter, by investing in a lot on robotics. So on the top middle picture, so you can see the size of the robot, the welding robot as relative to the human that is. So we are talking about huge robots for shipbuilding. And then we also implemented drone for. So these are all part of the whole digital production process. So if we look at linking digital production to the other part of the process, for example, digital design, and then we also offer digital solutions. So by linking them together, it actually enabled us to have integrated digital design, production, as well as a solution. So in the maritime or marine offshore sector, certification are very important. I mean, likewise in a lot of other industry that was mentioned many times. So I'm glad to share that Sembcorp Marine is one of the pioneers in trying to implement additive manufacturing in the marine and offshore sector. Just to give an example, so we have got the first certificate from DNVGL for applying 3D printing. Basically, we try some 3D printed parts to be installed in our own equipment and machineries. These are some of the gears. And before we want to actually recommend to customer, right, we need to try out and be confident ourselves in the technology. So we actually tried it out, and then we got the first certification from DNV. Following which, we have also started to engage our customers, who come to the shipyard, to recommend them to 3D printed parts. And then some of them, the more forward-looking one, for example, on the left-hand side, one of the first applications which we successfully implemented on board a polar tankers, which is a US-based shipping companies, and got the certification from ABS to approve. So the part was actually printed, put on the vessels. After a few months, we took it out, and then it was inspected by the attending surveyor and the chief engineer, and they are very happy with the outcome of the printed parts. So some of the key benefit and challenges of AM, I'm sure all of you are the experts here in AM, so I'm more talking about particularly in the area of implementing AM in the marine and offshore sector. So the benefit in a ship in particular, ship is always moving around, carrying cargo. So every downtime, it has to be minimized. So whenever there's any parts that broke down, you need to quickly change the part. And what if the part is not available in the warehouse? then you have to ship the parts from, let's say, a different part of the country. So you do not have the luxury of time for the entire vessel to idle and wait for the parts to arrive. So for that, 3D printing offers this advantage of on-demand printing, so that it can quickly replace the parts so that the ship can carry on to do its business. So production on demand, that's of course what I also added. So this will help to reduce the logistic cost, the inventory cost for customers, for shipping owners and operators to store their parts in various parts of the world. Another benefit is, of course, 3D printing parts are very suitable for highly customized and complex parts. And then, of course, we have also the advantage of design freedom, which is not limited to the standard size material. So the limitation, I would say, in scaling 3D printing in the marine sector and offshore sector, first is the cost. So in general, what we see, the costs are still relatively high, about 20 to 50%, as compared to conventional part. So there's this cost barrier that need to be overcome. There's also this IP issue for OEM parts. Of course, we cannot just happily go and print any service bureau to print OEM parts. This is, of course, then. So for now, the parts are mainly confined to the obsolete parts, for example. And then, of course, 3D printing needs post-processing. There's a lack of, and I think most importantly, the lack of large format AM technology. So what I want to say here is for 3D printing to be relevant, to continue to be relevant in marine and offshore sector, size matters. So it's important, to have large format AM technologies in order for AM to be scaled in this area. Okay, so I will share with you 3 opportunities here in terms of how for 3D printing in the maritime and offshore sector. First of all, I think this is something that's quite interesting that I observe. There's increasingly a lot of solutions that is coming up that offers a digital spare part or digital supply chain for ship parts. For example, you can see some examples of Williamson, and then there's also another example, shipparts.com, where they offer ship owners the flexibility to of course, one is that you can have a library, digital library, to keep the parts in terms of the geometry. Then, wherever the ship goes in the different port of course, if it requires printing, then the service bureau, of course, in the different location can print the parts, and then you can replace it in wherever the ship goes. Another adjacent, which I thought is also very interesting to share, is that there's also this part on the last mile. That means because in Singapore we have more than 2,000 over vessels that transit or stationary waiting to enter the ports in Singapore at any point of time. So there's always this interest or to have the part delivered through using drones, for example, the 3D printed parts that can deliver to the vessel waiting at the anchorage. Second opportunity is I have give 2 examples here. For now, just like I mentioned, 3D printed parts are focusing a lot on functional parts, but there are also opportunities when you apply it to the offshore sector. It can also be used for a structural component. For example, I give 2 examples here. You can see there's a semi-submersible vessel that we have. This is the world's largest semi-submersible vessel that we delivered to Sleipnir, to Harima. So the vessel is called Sleipnir. So it's a very huge, it's 2 by 10,000 ton lifting capacity. So what is interesting is that as part of the leg structures, there are more than 50 the corner joints. Currently is casted. Okay, and what is interesting is that these 50 corner joints are all different shape and sizes. So if you can imagine using casting technology to cast 50 over different parts is very expensive, So 3D printing does offer the advantage and opportunity for such parts. And then we have another example at the bottom. There's an example of FPSOs. We have module supports. So currently it's using pipe and plates to weld together, traditionally method. So we can also use 3D printing to be applied for this in this application. I just want to also mention here for 3D printer part to be applied for a structural component, we have to also consider in terms of the strength of the surrounding structure. So it's more of a global analysis than just a local for functional parts application. Okay, finally, the third opportunity, the redesign for additive manufacturing. I think there is huge potential. In particular, I would think that this requires a paradigm shift in terms of how designers actually design offshore structures instead of using pipes and plates, brackets, angle bars. We can actually use 3D printing to improve the performance and reduce wastages as compared to conventional printing. In conclusion, AM is a game changer for the marine and offshore. It's able to deliver faster turnaround time, enable mass customization. AM is, in terms of the relevancy, is currently being used in partial repair and replacement of functional parts. It's excellent for printing of obsolete parts. Opportunity, as I have shared just now, digital spare part. The large, so size. Okay, I cannot emphasize further. So it's very important to really look at the, to invest and to really look at how we can print larger parts in a more efficient and a cost-effective manner. And then the last one is a design for AM. With that, thank you very much for your attention.
Hock, thank you very much. And you may take your seat, please, and then we'll bring you back later on to answer audience questions. And dear audience, indeed, we are definitely interested in getting your questions for our speakers, so please send them to us either online or people in the room. We will certainly take your questions from the room also. And now we move on to Dr. Tian, who joins us from Deep Blue Aerospace. And she was unable to be with us live online, but she has sent us this presentation.
Hello, everyone. I'm Tian Cailan from China. I obtained my PhD at Tsinghua University. I'm now working at Deep Blue Aerospace and in charge of 3D printing-related applications. Today, I'd like to talk you through the applications of 3D printing at our company. This presentation will consist of 3 parts. First, an introduction to Deep Blue Aerospace. Secondly, the applications of 3D printing at our company. Thirdly, our company's way forward. Now, let me jump into the first part. First, let us watch 2 short videos about our company and our rocket tests.
我们是江苏生态航天有限公司，我们公司的主要任务呢是专注于可回收液体运载火箭的研发。我们从18年开始就瞄准这个目标，一直在前进。今天呢，我们在进行入轨火箭，也就是我们最后100吨级的这个火箭的雷霆20发动机整机实验，它是我们这一款入轨火箭动力的核心。 此次试车的成功，也代表着我们之前所有的设计都是一个正确的方向。这次点火实验的成功，标志着我们已经具备了研制20吨级的液氧煤油火箭发动机的能力，也标志着我们的发动机的研制从方案阶段转入了出量阶段，为我们后续入轨火箭的研制奠定了基础。5、4、3、2、1，点火！
1、
Next, I will talk about how we leverage 3D printing at our company. Due to its technical advantages, 3D printing is widely used in healthcare, transportation, aviation, and aerospace industry. Compared to conventional machining, 3D printing is more tailored to manufacture parts with complex shapes, materials, and features, enabling a significant cost reduction. The picture at the bottom left depicts a supersonic airplane launched by the American company Boom Supersonic in 2020. 21 parts made of titanium alloy are 3D printed using sapphire printers from Velo 3D. Most of them perform critical engine operations. This picture at the bottom right displays a commercial jet born out of a cooperation between Saffron Group and SLM Solution. Its 3D printed nose landing gear has a size of 455 by 295 by 805 millimeters. It is the very first time that SLM technology has been used to produce such a large component. It proves the feasibility of 3D printing aircraft parts using SLM technology. Traditionally, landing gears are made of 3 parts, manufactured separately by 5-axis machining. An overhaul to the parts design was made to adapt to 3D printing technology, with a weight reduction by 15%. Among all possible applications, metal 3D printing technology is born for aviation and aerospace industry. Due to the high raw materials and equipment costs, metal 3D printing remains costly. The cost sensitivity of other industries has strongly limited the usage of metal 3D printing in the respective field. Whereas in aviation and aerospace industry, price is not the biggest concern, weight is. 3D printing can manufacture lightweight components with complex structures, reducing weight and thus fulfilling the ultimate pursuit of our industry. Let's now look at several cases of 3D printing in the commercial aerospace industry. Launcher is an American startup specializing in small-sized rockets. Using 3D printing, it is constantly upgrading the performance of its rocket engine, aiming to manufacture highly efficient and low-cost rockets that can send satellites into the orbit. Founded in 2017, Launcher started to develop 3D printed parts for E2 engine. E2 is a closed expander cycle, high-efficient 3D printed rocket engine. Its turbo pump, combustion chamber, and other major parts are all 3D printed. The combustion chamber is made of a copper alloy and is fabricated on M4K 3D printer from AMCM. The integration of highly complex cooling channels substantially increases the engine's cooling efficiency. This combustion chamber is the largest part of its kind, boasting of a 860 mm height and a 410 mm diameter. This year, on the 21st of April, this engine was successfully tested at the NASA Stennis Space Center. During the test, its turbo pump reached 30,000 RMP. After the test, the throat of the combustion chamber remained in its perfect shape. According to Launcher, 3D printing can push the performance of an engine to its limits. Another outstanding example is the American company Relativity Space, specializing in liquid rocket launch. It is the first launcher in the world that 3D prints the entire rocket using the largest metal 3D printer that has ever been built. Using SLM and WAAM 3D printing, the company builds rocket engine and propellant tanks. significantly simplifying the supply chain. Part count is reduced from 100,000 to less than 1,000, build time from 24 months to 2 months, design iteration from 48 months to 6 months. Its ultimate target of applying 3D printing is to reduce part count and increase launch reliability. Engines such as Iron 1, 2, VAC are all 3D printed. Through cutting part count in combustion chamber, igniter, turbopump, reaction control, thruster, and the vehicle pressurizing system, the reliability of engine's performance is improved. Iron engine tests have been completed more than 500 times using liquid oxygen and liquid natural gas as propellant. Most of Deep Blue's 3D printing applications are based on SLM enabled by metal powder bed fusion technology. 80% of our engine parts are 3D printed. Now let me take the production of nozzles as an example. The production of nozzles uses the same technology. Though faced with multiple challenges during design and manufacturing, through the detailed calculation, well-aligned coordination, and process testing, we have addressed these challenges one by one. The height of this product in the picture is 800 millimeters. The successful printing of nozzle is closely related to 3 aspects. First, the close alignment between design and process teams. Secondly, the cross-functional cooperation ensures smooth manufacturing. Colleagues from process and operation teams make concerted efforts in various fields, from the design of supporting structure over the identification of risk areas to post-processing. Thirdly, forging constructive partnership with equipment providers. Our large format 3D printer FS621M with open source control system is provided by Fosun with an external dimensions measuring 620 by 620 by 1,100 millimeters. Fosun can independently design and produce printers. Our choice is its full laser printer with industry-leading efficiency and speed. We highly appreciate the detailed training and supporting equipment offered by Fosun, which makes the efficient manufacturing of engine nozzles possible, which substantially reducing part count and improving the reliability. How is 3D printing implemented at Deep Blue? The seamless integration of 3D printing into Deep Blue is owed not only to technological progresses and advanced process design mindset, but also to our leaders' foresight to resolutely drive the 3D printing forward. Experienced technicians, managers, and factory workers specialized in 3D printing are devoted to development, process management, quality control, and validation of our products. We adopted an open mindset. To meet various KPIs, we take the properties of 3D printing into consideration by combining parts, enabling higher design efficiency and engine performance. We also adapt our design to process, simplifying the production. With our management's recognition of the great potential of 3D printing in accelerating the design iteration, we are encouraged to take bold steps to drive the development forward. Finally, let us look at Deep Blue's way forward. 3D printing finds extensive application at Deep Blue, with further potentials to be tapped into. However, some technological challenges have also emerged. Going forward, Deep Blue will allocate more personnel and financial resources to further explore advanced applications and to tackle known and unknown challenges.
And that was Dr. Cailan Tian from Deep Blue Aerospace. Let's give her a round of applause, even though, of course, she was appearing there on tape. And we are now joined by Dr. Guoying Zheng. She is with the Singapore-based company ST Engineering, and she also joins us virtually in person. Welcome, Dr. Zheng. The floor is yours.
Thank you. Okay, in the first place, I would like to thank the organizer to invite us. So today I'm very pleased to share one of the case studies of our delivered projects in 2020. I don't have the slides to show the company introduction. However, you're all invited to visit our website. I just have a very quick introduction of the ST Engineering, our parent company, who's an international company, has commercial, public, and the defense business across over the world. So the business areas covers aerospace, satellite communications, smart city, land transport systems, and marine systems as well, digital systems. So particular for this case study is from the commercial aerospace sector. I really stick to the organizers' suggested agenda. So let's deep dive into one of the case study from the real applications which we delivered. So as a start, I just retouch on the AM advantages. Many of the prior speakers has already mentioned about the advantages of AM. So let me touch a few, the outstanding ones. For example, AM is able to bring the digital file to the world, make the digital manufacturing feasible, which means instead of a physical warehouse, we just have the digital warehouse where we can just print on demand close to the point of use, which really is disruption to this current supply chain in the world. So this project indeed demonstrating the resilience of AM in terms of the supply chain disruption. Later I'm going to share more on that. And the freedom bring by the AM in design allow us to combine the parts, also combine the function together. And additionally, we also can combine different current manufacturing segments into one single one, which is the additive manufacturing, that actually allow us to shorten our supply chain. As a result, we have a more durable parts, we have lower part life cycle, life cost, make the customization easier. So without others, we move on directly onto the problem statement. So here is the problem statement where customer require us to integrate these three medical equipment onto the stretcher, which appear on the air ambulance. So there's nothing provided other than these three equipment. If you look at the traditional way of the stretchers integrated with the medical equipments, this is something we look familiar. The impression is bulky as well as difficult to make the equipment mobile following our patients who is supposed under intensive care. So our customers required efficient monitoring of the patient's condition by any of the crew on board. Usually this a crew likely sitting on the passenger seat just by the side. And the installation of these equipments not form any obstruction for the doctors to maneuver around to take care of the patient. And also they require the seamlessly mobility of the equipment following the patient in and out when they need to be transported around. But lastly, they also wanted the equipment to be easily handled by all the doctors, including female doctors. So what we have achieved, you look at the middle top picture shows the stretcher. We have three equipments installed over there. The center of the displays are aligned, which allows the observer to easily monitor all the three equipments and same glance. So in this height of the equipment design, we cater for 5% female to 95% tau male observers, which covers large observer populations. At the same time, you can observe the installed equipment indeed is pushed away from the stretcher where the patient lies, so which gives the maximum space for the doctor to do the operations, as well as no obstruction in moving the patients in and out. At the same time, we introduced the quick release, which is 30-second install and removal of 3 sets of the interfaces without any tool, no need any of the tools, just by bare hands, which is between the equipment to the mount, between the mount to the stretcher, as well as the battery to the equipment. So that actually gives the total mobility for the operators to manage the equipments. We also introduced the feature called cage design, which no need any interface between the mount and the equipment, so which give a lot of freedom for the customers to choose the equipments they wanted to introduce. We applied the topological optimization. The aim is to strip away any unusable structures. So the mount we delivered is really lightweight, is about 1/4 of the payload weight, although it's cantilever structure. Additionally, we certified these mounts to the A330 aircraft specifications, which is fully certified to the airworthiness requirements. Now we are ready to print this kind of mounts from digital file while customer in demand. So this is what we are achieved. This mount has been utilized as a demonstrator for many exhibitions because it shows a lot of dedicated AM advantages. Over here, if you look at the milestones we achieved, you may have some comments. For example, we completed the prototype in the 7 months. Then in the following month, we finished proof load test in all 6 axes. And the next month, we achieved airworthiness approval. We delivered in the 1-year mark. There's no delay. The point I wanted to mention, this 12 months 1-year mark delivery is just happening during the pandemic lockdown period in Singapore in 2020. So we managed to deliver it on time. Really is a demonstration showing that AM is resilient to the disruptions to supply chain. And this allows our customer to commission the flight services in 2020, which is reported in the news. Some of the pictures are put here. So this is the recognitions and the public response we received for this project. I'm using these slides to summarize the key steps we have gone through to bring the concept to a final airworthy products in the operation. So over here, you can briefly see that 2 tracks are parallel. One is talking about AM processes certification and the production qualification controls, as well as a demonstration of compliance. On the other hand, showing the development from the very beginning topological optimization. You can see the shape and the left bottom is very organic, and use that to find our best efficient path to come out of a design. Then we utilize the FEM to confirm the design integrity, which based on the qualification design values of the AM systems. So from there, we 3D printed prototype parts and we use it to use for the design review, which make it much easier for our customers to check the interfaces, the installation aspects, as well as the performance. So we are able to achieve the design confirmation in an earlier time as compared to conventional way. We use CAD models, paperwork to clear the design review. At the same time, you can see on the right, we do the coupon test. We cater for various variables in the AM processes from the raw stock differences, from the locations in the chambers, as well as the shape, the orientations, to ensure the process which we defined is robust enough to guarantee the performance. At the end of the day, we achieved. Then from there, we move on to optimize the printing. When we do the design, we already think about the printing, the orientation of the print, the support structure potentially we needed. So when we move on to the printing step, we already have that considered. If you look at the picture and the second row, we actually nesting the parts together, even vertically, and confirm the quality of the production. We always print the witness coupons, so which we are tested to, making sure we achieved intended design values. After we completed assemblies, we do the operational acceptance test to ensure that the surface, the interface mapping is achieved, the installation and the release is shorter than 30 seconds without any tool, just use bare hand. And the top right corner, which shows we have done the full scale loop test, is a proof loop test to ensure that everything we have done is meeting the structure integrity. So with all this effort, we qualified the parts as airworthiness part. If let's say we comment onto the scaling challenges and what kind of solution we may bring. So the challenges we actually, based on our experiences, there are two big aspects. The first thing is the AM, particularly for the processors. AM qualification depends on criticality of the parts. When the parts demand for different safety gear, we will need different way of showing compliance. For example, damage tolerance, fatigue, safe, and so on. And also the environment-related aspects. So that's the first part. The second portion, when we qualify the processors, we have to define the AM processors with taking into the material controls, machine control. When we qualify the machine, is by serial number. It's not part number alone, it's a serial number. And also associated the post-processing, such as heat treatment, which has direct impact to the performance of the printed parts, as well as the printing parameters. How should we control it? How should we monitor the changes over the time? So that's for the second aspect. The third aspect is adequate inspection means of printed parts. We not only need to look at the surface, we also need to look at interior. What kind of porosity, what kind of patterns is acceptable in order to achieve intended design values. In addition to this, we have to look into the practical aspects. For example, how do we do the support removal? The support removal is not only affect the parts performance, also contributed to the constant quality over the years for the production. We also need to look into the suitable surface treatments to give the parts sufficient protection to achieve intended functionality. That portion is also we have to consider the cost. Last not the least is the assembly and the final inspection. So this is very much in the practical aspects. Unfortunately, as compared to the traditional manufacturing means, additive manufacturing is still lacking in both of these two areas. We are still in the development phase or the enhancement phase to bring this to the practical applications. To overcome the lacking in both of these areas, commendable investment together with effective supply chain or our ecosystems is necessary. So in order to scaling up, we feel that sufficient demand of the same type of AM, the prior speakers mentioned about AM indeed is a regime. There are plenty of different methods, different machines, right? So over here we are talking about the same type of AM. complete and efficient ecosystems are the key aspects for scaling. So demand and the readiness is two aspects. They have to be ready for us to scaling the AM applications. So this project indeed is a demonstrated showcase for the AM advantage. Just now I mentioned the very early page. We realized topological optimizer structure design. This may not be possible for conventional manufacturing means. And the customization appear to be easier because there's no additional cost or efforts. Consolidation of the parts to achieve the lightweighting is demonstrated. For example, the bar, the U-bar we created, which is able to attain two-directional loads and more resilient for supply chain disruption. So this is demonstrated through this project. And the takeaway in terms of learning points we would like to share, making the EM parts for aviation applications, we really have to think about the following. Highly integrated workflow for the holistic way designed for AM. Not only functionality, not only manufacturing strategy, but also how are we going to demonstrate the compliance to really have an airworthiness part in end of the day. A complete value chain to drive the solution is very practical and the important aspects. Effective inspection program, which equally important to assure the integrity of the part we deliver to the customers. Full traceability based on the EM know-how is very important not only for the quality, also for us to learn to further enhance and mastering the EM processes. So this is the last slide. You all invited to visit our website. I just briefly mentioned that in commercial aerospace, we are the DOA and the POA is granted by the EASA as well as our CES. We have a full range of cabin interior products which carry the EASA certification, CES certification, as well as the FAPMA. So you're welcome to visit our website. Have any interest, we can further exchange. Let's work together. Thank you.
Thank you very much, Dr. Zheng, and you're getting a nice round of applause here. Stay with us, please, because I want to see if we can just take one or two audience questions very briefly. And Dr. Ang, if you would please also join me back on stage. Then let's see if we have, I do not see any questions coming in online yet. Do we have a live question in the room, either to Dr. Ang or to Dr. Zheng? Come over here with me in the light, if you would. Anybody? Then I am going to ask both of you to please, very briefly, because we are just about out of time and we're standing between our audience and their lunch break, but I would like to come back to the overarching topic of the regions and ask you, I'll start with Dr. Ang and then go to Dr. Zheng, what you think is different about APAC when it comes to AM. What makes AM particularly promising in Asia, or what particular challenges would you say are in Asia that are perhaps different from those in other regions? Dr. Ang?
Probably I can explain from the marine offshore perspective. I mean, shipping is a global business. So essentially, whatever we are doing, it actually is in terms of the requirement, is similar worldwide. So I don't see any particular differences in terms of having 3D printed parts to be installed on the vessel, for the examples that I have shared. So yeah, because the vessel traveled to the US, traveled to Europe, traveled to China, traveled everywhere. So essentially, for application in marine offshore, I do not see any particular difference in terms of the different regions.
Mm-hmm. Thank you very much. Dr. Zheng, I will come to you with that same question, but I also have a question that has come in from the audience, because you were quite direct about the challenges that you have faced at ST Engineering. So maybe you can just tell us, the audience member asks, what was the hardest nut to crack?
Okay, thanks for that question. AM is very novel. So when we firstly wanted to apply AM, the first concern is the safety, and especially without the services track record. So that really is a valid question. So I would say the hardest nut to crack is to convince the users comfortably to accept your AM solution.
Mm-hmm. Thank you. Do you have any thoughts on that, Dr. Ang?
No.
No?
Yeah.
Okay. Hardest nut for you to crack?
Okay. I think in terms of the challenges, really for 3D printing, I think I've mentioned earlier, for it to scale in terms of our application, the cost has to come down. One. Second, if I can relate why, because I noted I've been sitting, I've joined since yesterday. There are not much mention about marine and offshore, 3D printing being applied in marine and offshore, really because I can understand, really because the current concentration, there's a few niche industry has been shared earlier, medical, aerospace, blah, blah, blah. So these parts, I would say, they are mainly smaller as compared to marine and offshore. So really, for it to have, hopefully, in the subsequent AMTC, we can have more mention, more example of marine and offshore. If we have more large format printing technologies that are more ready for us to apply, I think this is something that will really be very important. So cost, second is the large format printing.
Thank you very much. And just very briefly back to you, Dr. Zheng, because I didn't manage to get your answer on the other question of what is unique about Asia when it comes to AM. Very briefly.
Okay, I think the AM actually bring the world closer because we are doing digital manufacturing. So in that way, indeed, Singapore is a small country. Indeed, we see ourselves have more opportunities. This part of the world is quite fast growing, especially in aviation. So we think we are probably, AM is a very good manufacturing way, connect us better with the rest of the world. So that's what I would like to comment.
Thank you so much for being with us. Dr. Zheng online, Dr. Ang here with us in person. Many thanks for being with us today and for your very, very interesting and very concrete use cases there. Again, let's give them a warm round of applause, please, ladies and gentlemen.